Hello friends, let's start off with Miscellaneous Exercise Chapter 2, Relations and Functions. So in this first question is the relation f is defined by f of x is equal to x square where x lies between 0 and 3. It's including 0 and 3, and then it's equal to 3x. Over here it's equal to 3x when x lies between 3 and 10. And here you can see that it is 3 when x square is equal to it's equal to x square. It is taking x is taking value of 3 also, and when it is 3 it's again taking value of 3x. So we'll see what is the value which we get when we draw the table. We'll see that. Then we also define a function. The relation g is defined by g of x is equal to x square such that x lies between 0 and 2. It's including 0 and 2, and it's equal to 3x if x lies between 2 and 10. It's including 2 and 10. So show that the function show that f is a function and g is not a function. So we know that here what is a function and what is when it is not a function. So here if x is repeated twice and it is mapped on to the same element, then it is said to be, it is not a function. If it is mapped on to two different values of y, then it is not a function. So we'll just see here over here what we have defined solution. In this solution we have that what is f of x given as f of x is equal to x square when x takes all values between 0 and 3, and it is equal to 3x when x takes values between 3 and 10. So we'll see whether this is a function or not. We'll just draw a table for this. We'll take x and f of x over here. So in this we can see that what are the values it takes. So when you can see here what are the values between 0 and 10 it lies. So you can write from here 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. So these are the values x is taking. So when x is 0, what is f of x? It lies between 0. This x lies between 0 and 3 means it's x square. So here you are going to get it as 0 square, that is 0. Then when x is equal to 1, f of x is equal to 1 square, that is 1. When x is equal to 2, you can see that here it is 4. So still here it takes, and when x is equal to 3 also it takes x square. So therefore this is 9. So up till here from 0, 1, 2, 3 it is taking x square. So this is all x square which we did. Now we'll see from here again it is taking from, it is including even 3 from here, and from here to here it is taking 3x. f of x is taking the value of 3x. So now you can see here again when x is equal to 3 over here, 3x means 3 into 3 is nothing but 9. So this is satisfied. Then when x is equal to 4, what are you getting? 4 3s are 12. When x is equal to 5, 3 5s are 15. When x is equal to 6, 3 6 are 18. Then 3 7s are 21. Then 3 8s are 24. 3 9s are 27. 3 10s are 30. So you can see that all the x values, they are not repeated, and also they are having a unique image for onto f of x. So therefore here this is said to be a function. Y values are the range, so domain and range. So it is very clear that since every point of the domain has one and only one image under f, this relation is a function. See from the problem, g of x is equal to x square when x lies between, here you can see when x lies between 0 and 2 it is equal to x square. When x lies between 2 and 10 it's equal to 3x. So we'll just see what's the problem about. So therefore we'll define what is g of x. So g of x is equal to x square when x lies between 0 and 2, right? And it's equal to 3x when x lies between 2 and 10. So we'll see how this, when we form a table, how do we get the images, we'll see. So therefore here you can see what is x and what is g of x. So when x is taking values 0, 1 up till 10 we are having, because this is from 0 to 2 and here you are having from 2 to 10. So totally the domain is from 0 to 10. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? So now therefore here you are having when x is equal to 0, what is g of x here? It is 0 square means 0. Then if it is equal to 1, 1 square means it is 1. Then 2 square is 4. Then here till here it is taking x square. Then again when x is equal to 2, it is again taking 2 to 10, it is taking 3x. So now here you are getting two images. When x is equal to 2 over here, 3 into 2 is 6 you are getting. So therefore next you are getting 3. 3 into 3 is 9, then 4 3s are 12, 5 3s are 15, 6 3s are 18, 7 3s are 21, 3s are 24, 9 3s are 27, 3 10s are 30. So now here you are having that, you can see that in this you are having 2 is mapped onto two different images. That is, it is not having a unique image, it is having two different images. The same element of x is having two different images in g of x. Therefore this is not a function. Since every point of the domain has, it does not have a unique image on g of x, therefore this is said, this relation is not a function. So we can see from this table very clearly that therefore 2 in the domain of G and the image of 2 under G is not unique. It is having two different images. So since 2 4 and 2 6 both belongs to G, therefore G is not a function. So f is a function because all of them have, here there is only has one and only one image under f, but here they have, it is having two images. This x under G, it's having two images, that is 2 is mapped onto 4 and also onto 6. So since 2 4 and 2 6 belongs to G, therefore G is not a function. 2 in the domain of G and the image of 2 under G is not unique. So going into the second one. So now in the second problem we are having, if f of x is equal to x square, find what is f of 1.1 minus f of 1 by 1.1 minus 1. So what are we going to get? We'll just see here. It's equal to solution. What is given to us here? It's given that f of x is equal to x square and f of 1.1 minus f of 1 by 1.1 minus 1 is what? So this can be written as f of 1.1 is nothing but 1.1 whole square minus 1 whole square divided by 1.1 minus 1. So here you can write this as, this is a square minus b square, means you can write it as a plus b into a minus b. This is a minus b into a plus b divided by 1.1 minus 1. So when you are writing this 1.1 minus 1, this also you can write it in this way. So this and this will get cancelled. So you are getting it equal to 1.1 plus 1, which is equal to 2.1 is the answer. Next. Third problem, find the domain of the function f of x is equal to x square plus 2x plus 1 by x square minus 8x plus 12. So now here in this, what is the function given? We have to find out what is the domain of here. It's equal to x square plus 2x plus 1 divided by x square minus 8x plus 12. You can see that this is a rational function. So here f is a rational function. And this is defined, and now here the domain of f is nothing but it is all set of real numbers minus of the denominator should not be equal to 0, isn't it? So therefore it will take all real values except the denominator part, that is r minus of x, such that x square minus 8x plus 12 is equal to 0. When this is equal to 0, it is not acceptable. That means it is not in the domain. These values, that is r minus of, we are taking this minus of only this function whichever we have written here. So therefore this is equal to, you can write this as equal to r minus of x, such that here what are the factors of 12? You can take it as 6 and 2. So x square minus 6x minus 2x plus 12 is equal to 0. So which is equal to r minus of x, such that x into x minus 6 minus 2 into x minus 6, which is equal to 0. Therefore this is equal to r minus of x, such that x minus 2 into x minus 6 is equal to 0. So when x is equal to x minus 2 is equal to 0 and x minus 6 is equal to 0, so which is equal to r minus x, such that x is equal to, here you are going to get it as 2 and 6. So other than this two values 2 and 6, it will take all the values, that is r will take all the values. So we can just write it down in this way, r minus of 2, 6. This is the domain of f. Next we'll go to fourth one, find the domain and range of the real function f defined by f of x is equal to root of x minus 1. So now here for the solution part, you have that f is a real function only when x minus 1 is greater than or equal to 0, because under root we are taking, we should not get negative values. Therefore that is x should always be greater than or equal to 1. So therefore domain of f will be equal to 1 to infinity. Then now y is equal to f of x. For finding out the range, we'll see it's equal to root of x minus 1. So clearly you can see that because x minus 1 is greater than or equal to 0, so y is also greater than or equal to 0, which means that y square is equal to x minus 1. That means you're squaring on both sides, so you're getting it equal to this, or x is equal to 1 plus y square. So since x is real for all y belongs to R, you can take this as the first equation and this is the second equation. Since x is real, you can see that because it's 1 plus y square and y is greater than or equal to 0, therefore range of f is the set of values common to 1 and 2. So therefore range of f is equal to y, such that y is greater than or equal to 0 and y belongs to R means, so what are you getting? It's equal to 0 to infinity. This is the values it is taking. Because it's greater than or equal to 0 we are taking here, but here for x domain is 1 to infinity, for range it is 0 to infinity, because you can see over here we are taking common both y greater than or equal to 0, we are including 0 there, and y belongs to R means all the numbers from in R which are greater than or equal to 0, that is to infinity. So therefore our range of f is 0 to infinity. Next we'll go to the next problem. Fifth problem. Find the domain and the range of the real function f defined by f of x is equal to mod of x minus 1. So in the solution what do we have is, over here we can see that for all x belongs to R, f of x is a unique real number. So over here you can, x can be any value, that is therefore domain of f is equal to R, that is any real value. Then we have to define what is f of x. F of x is a unique real number. So when you put negative value, what we get? When we put positive value, you will get a unique value over there. So therefore next we are having over here also, for all x belongs to R, mod of x minus 1 is greater than or equal to 0, which implies that f of x is greater than or equal to 0. Therefore range of f is equal to, here you can see that it follows from 0. If you are taking a negative x value over here, when it is in mod or if it is an absolute value, we will get it as a positive value, that is it's greater than or equal to 0. So therefore it takes range of f is nothing but 0 to infinity. I'm sorry, here infinity is closed. So in this way you can write this. Now going into the sixth problem. What is the sixth problem? Let f be equal to x comma x square by 1 plus x square. X belongs to R, be a function from R into R. Determine the range of f. So here in the solution part, what we have is, here we have that y is equal to f of x, which is equal to x square by 1 plus x square. So this is given to us. Now we have to find out what is the range of f. So if we take this as equation 1 over here, so from 1 we have that y is equal to x square by 1 plus x square is greater than or equal to 0 for x belongs to R, since over here x square is greater than or equal to 0. And again from 1 we have, again from 1 we have y is equal to x square by 1 plus x square. We add and we subtract 1 for this, so it will be equal to y is equal to x square 1 plus x square minus 1 by 1 plus x square. We are adding a 1 and subtracting 1, so which can be written as 1 plus x square by 1 plus x square minus 1 by 1 plus x square. So this is equal to 1 minus of 1 plus x square. Now here for different values of x over here, what do we get? We get this value is less than 1 for all x belongs to R. So we'll take this as equation 3. This we'll take it as equation 2. So we're having 1, 2 and 3. So now from 2 and 3 we can write what is the range. From 2 and 3 we can see that y is greater than or equal to 0 and y is less than 1. So therefore y, which is equal to f of x, lies between 0 and 1. So therefore the range of f is, f of x is equal to, it is including 0 and excluding 1 over here. So it is open in the one side and it is closed near 0. So it's including 0 and it is excluding 1. And it lies between 0 and 1. So going into the 7th one, let f comma g such that be defined in such a way that r to r be defined respectively by f of x is equal to x plus 1, g of x is equal to x minus 3. Find f plus g, f minus g and f by g. So in the 7th problem what we have is let f comma g be such that they are defined from r to r. Let fg from r to r be defined respectively by f of x is equal to x plus 1, g of x is equal to x minus 3. Find f plus g, f minus g and f by g. So in the solution part we can see over here. What is the solution? We'll see here. It is defined first. What is f defined as? We'll see here. So f of x is equal to x plus 1 and g of x is equal to 2x minus 3. So now what is f plus g? F plus g of x is equal to f of x plus g of x, which is equal to x plus 1 plus 2x minus 3, which is equal to 3x minus 2. Next, f minus g of x is equal to f of x minus g of x, which is equal to x plus 1 minus of 2x minus of 3, which is equal to x plus 1 minus 2x plus 3. So you are going to get it as x minus x plus 4 or 4 minus of x. So this f minus of g of x is equal to minus x plus 4 or 4 minus x. Now what is f by g of x? We'll see. It is equal to f of x by g of x, which implies g of x is not equal to 0. So that means here you are having x plus 1 divided by 2x minus 3. So 2x minus 3 is not equal to 0 means x does not take the value 3 by 2. So this is equal to x plus 1 by 2x minus 3 for x not equal to 3 by 2. So these are the values of f plus g, f minus g and f by g. 8th problem. Let f be equal to set of all ordered pairs 1 comma 1, 2 comma 3, 0 comma minus 1, minus 1 comma minus 3 be a function from z to z defined by f of x is equal to ax plus b for some integers a, b. Determine a comma b over here. So now in the solution part, what do we have here? We have given f of x is equal to ax plus b. So now we know that here 1 1 belongs to f. So which implies that f of 1 is equal to 1. So replacing x by 1, we'll take this as equation 1. In equation 1, what do we get? We'll see. We have f of 1 is equal to a plus b, that is a into 1 plus b, which is equal to a plus b is equal to 1, since f of 1 is equal to 1 over there. Now we know that f of 2 is equal to 3, f of 0 is equal to minus 1, f of minus 1 is equal to minus 3. So all these values we have. Now also 2 comma 3 belongs to f. So which implies that f of 2 is equal to 3. We'll take this as equation 2. So therefore here you will get f of 2 is equal to a into 2 plus b, which implies that 3 is equal to 2a plus b. We'll take this as equation 3. Now we can solve for a and b from equation 2 and equation 3. So we'll write down both the equations. A plus b is equal to 1 and 2a plus b is equal to 3. So subtracting these two equations, subtracting equation 2 from equation 3, what do we get? So 2a plus b minus of a plus b is equal to 3 minus 1, that is 2a plus b minus a minus b, which is equal to 2. So b will get cancelled, which implies that a is equal to 2. Now substitute the value of a in. Now substitute a equal to 2 in a plus b equal to 1. So therefore you get it as 2 plus b is equal to 1, which implies b is equal to 1 minus 2, which is equal to minus 1. So therefore a is equal to 2 and b is equal to minus 1 is the answer. Yeah, going into the ninth problem, let R be a relation from n to n defined by R is equal to AB such that AB belongs to n and A is equal to B square. So here A is equal to B square means if A is 2, if B is 2, then A is equal to 4. So in that way we have to take. So are the following true? A comma A belongs to R for all A belongs to n. A comma B belongs to R implies BA belongs to R. AB belongs to R, BC belongs to R implies A comma C belongs to R. So we have to justify our answer and we have to state which of the following is true or false. So here we can see from the first one, in the solution part, what do we have in the first problem? We'll just go into that. So here you can see that the first one is given as it is the set of all ordered pairs which belong to R for all A belongs to n. So if 1 belongs to n, that means A is equal to B square. That means if you are having A is equal to, suppose B is equal to 1, A is equal to B square implies that A is equal to 1 square. So now you can see that this A and B, that means A is equal to, you are getting again A itself. So here it's equal to 1. So A is equal to B. So A belongs to R. So only in this case we have that, we know that except natural number, but suppose if we are taking B is equal to 2, then A is equal to B square, which is equal to 4. So 4, 2 is the set which we are getting, but this does not belong to R, which relation we have defined over there. Therefore, so here you can write that we know that except natural number 1, none of the natural numbers is equal to its square. So therefore A does not belongs to R. It does not satisfy. It does not satisfy the condition A is equal to B square. So therefore this statement is a false statement. A belongs to R is false. So now what is the second one? We'll see. Second one we have AB belongs to R implies that BA belongs to R. That means the reverse part also should be belonging to R. So now from here we'll take an example and see very clearly. We can tell that it doesn't belong to R, because here if A is equal to B square, it does not imply that. So actually it is in the question, if A is equal to B square, that is if AB belongs to R, it implies that BA also belongs to R. But if here A is equal to B square, it does not imply that b is equal to a square. So therefore that is AB belongs to R implies BA belongs to R is not at all true, is not true, since we can see from this example if we take that, since A is equal to 4, B is equal to 2 and A is equal to B square, this is correct. So you are having here 4 2, but 2 4 does not belong to R since 2 is not equal to 4 square. Therefore the statement cannot be true. Now next, going into the third one. What is the third one which you are having? The third one you have AB belongs to R, BC belongs to R, means AC should also belongs to R. Here also we'll use one example and do. So now if AB belongs to R, it implies that A is equal to B square. If we take this as the first equation. Now if we have also if BC belongs to R, it implies that B is equal to C square. This is second equation. Now putting the value of B from 2 in 1, what do we get? A is equal to B square, means it's equal to C square, isn't it? So C square whole square means it becomes C to the power of 4. Therefore A is not equal to C square, because it should be equal to C square, then only we can tell that, which implies that AC will belong to R, but here it is not equal to C square. So therefore here you will be getting it as it does not belongs to R. So now if we take one example over here, that is AB is equal to 16, 4, which belongs to R, and BC is equal to 4, 2 belongs to R. Since you have for each pair A is equal to B square, but AC, which is equal to 16, 2 does not belong to R, since 16 should be equal to C square, that is 2 square. So it is not equal to 2 square. Therefore the statement is false. The statement is false. You can see all the transformations of A, B and C in this. Now the 10th problem, let A be equal to 1, 2, 3, 4, B is equal to 1, 5, 9, 11, 15 and 16, and F is equal to all the elements of A and B, that is ordered pairs 1, 5, 2, 9, 3, 9, 4, 5, 2, 11 are the following true. So you can definitely see that all the first elements are from A and all the second elements, that is 5, 9, 1, 5, 11 all are from B. So therefore here you can tell that F is a relation from A to B. So therefore in the solution part you can see that in the first one, every element of F is an element of A cross B. So this implies that F is a relation from A to B, since every subset of A cross B is a relation from A to B. We can very clearly see that here whenever it is defined, we have to define the relation in such a way that the first, that is the domain, should be from the first set and the range should be from the second set, the first component or second component, what we name them. So therefore here you can get, since every element of F is an element of A cross B, therefore we can say that F is a relation from A to B. And here you can see that all the elements of F, that is 1, 5, 2, 9, 3, 1, 4, 5, 2, 11, all these are from 1 from the first set, and the second one in the ordered pair is in the set B. That is domain and range, where it is very clearly defined in that. So now going to the next, that's the second, we have to show that whether F is a function from A to B or not. So here in the second part we have to show that whether F is a function from F. When you're taking this F, you can see that 2 and 9 and 2 and 11 both are having the domain the same, that is 2 2 is there in both of them. That means both belong to F, that is 2 9 and 2 11 both belong to F. But here you can see that F have the same first entry, that is 2 and 2. So the domain is the same for 2 of the entries. So here you are having 2 9 and 2 11 both belong to F, and here both these points of F have the same first entry. Since both of them have the same first entry, F image of 2 is not unique. F image of 2 is not unique. So therefore, which implies that F is not a function from A to B. So first one, F is a relation. Second one, it is not a function. Now in the 11th problem, we'll see what's the 11th problem. Let F be the subset of Z cross Z defined by F is equal to AB comma A plus B. AB belongs to Z. Is F a function from Z to Z? Justify your answer. So for general of, that is two numbers from Z, and then we have to do. So what is given over here? F is equal to AB comma A plus B. So the ordered pair is in this way, that is AB belongs to Z. So now if we take A is equal to 1, B is also equal to 1. So what do we get here? We have, what do we have? We'll see. AB means it is 1 into 1, and 1 plus 1, that is equal to, you're getting 1 comma 2. Now this belongs to F. Now again, if you're taking A is equal to, if you're taking first that, second we are taking A is equal to B is equal to minus 1. What we have? We have that AB is equal to, that is minus 1 into minus 1, then minus 1 minus 1. So you're getting it as 1 comma minus 2, which also belongs to F. So which implies that here what you're getting for 1, the first entry, you're getting 2 images. So the entry F image of 1 is not unique. It is not having only one image, it's having 2 different images. The same entry, you're having 2 different images. So therefore, which implies that F image of 1 is not unique, which implies that F is not a function. F is not a function. You're going into the 12th problem. You're having 12th problem here. Let A be equal to 9, 10, 11, 12, 13, and let F be from a function from A to N be defined by F of N is equal to the highest prime factor of N. Find the range of F. So here you have to find out what is the range of F. So here you have that A is equal to 9, 10, 11, 12 and 13, and F of N is equal to the highest prime factor of N. So here you have the prime factors of 9 is 3, which implies that f of 9 is equal to 3. So prime factors of 10 are what? 10 are 2 and 5. So which implies that f of 10 is equal to 5. The highest prime factor we have to take. So which is the highest? 5 is the highest. So we are taking prime factor of 10 is equal to 5. Then the only prime factor of 11, the only prime factor of 11 is 11 itself, which implies that f of 11 is equal to 11. Now we also have that the prime factors of 12 are, you can see that it is 2 and 3 are the prime factors. 4 3s are 12. So therefore the 2 and 3 you can take. So f of 12, the highest prime factor is 3. So the only prime factor, next what is the element which you are having? We are having 13. So the only prime factor of 13 is 13. So which implies that f of 13 is equal to 13. So therefore range of f is equal to set of f images of elements in the domain A. So which is equal to f of 9, f of 10, f of 11, f of 12 and f of 13. So now we have just now written what is the highest prime factor for each of them. So that is nothing but 3, 5, 11, 3 and 13. Because there is repetition of 3 and 3, we just write down it as 1. So 3, 5, 11 and 13. We are writing these two in 1 as 1. Because in a set you shouldn't have repetitions. Therefore this is the range of f. So range of f is equal to 3, 5, 11 and 13.